All right. So if you don't want to learn about how to monitor databases in general and Postgres specifically, you're in the wrong room, but I assume you're in the right room. So we'll go ahead and get started, and people can file in. So this is just for people who are going to watch the video online or whatever, so we don't need to look at that. The one thing I'll say is go ahead and ask questions anytime. Don't worry about interrupting me or anything like that. It's cool. I like to answer questions kind of in the flow. I know some speakers like to hold questions till the end, but I like questions to come in the middle. So this is our agenda today. I have a particular philosophy of monitoring, and I'm going to be going through kind of the philosophy, which is it's built over the last like 15 years of my career monitoring systems in general and databases in particular. And it's the foundation for why I formed a company called Vivid Cortex to give people great database performance monitoring. There is a big performance aspect of it, rather than just, is the system alive? It's also, is the system doing its job well? So I'm going to go through some of that, and then we'll wind up with Postgres-specific stuff at the end. There's not very much stuff that you actually should be monitoring about a database. There's several hundred things that you could, and there's lots of Nagios plugins that have 70 different options pre-configured, leading you maybe to believe that you should be setting alarms on 70 different things, and you definitely should not. So I'm going to spend the first part of the talk explaining kind of a way to break down this problem space of several hundred things and 70 option Nagios scripts and things like that into something much more manageable. And then by the end, I'll wrap up again with those specific Postgres things. So the first thing about monitoring a service like Postgres, a database in particular, is quality of service. Quality of service is everything that matters about database performance. Availability is not actually all that interesting. Availability is kind of table stakes, and in fact, if you don't have good quality of performance, then you essentially don't have availability. If your database is theoretically up and you can theoretically, connect to it and query it, but if it doesn't return results that are quick and consistent, then you essentially have an availability problem. So latency problems are availability problems. So I'm going to spend a few minutes talking about quality of service, what it is and why it matters so much, and how we can define it in a way that lends itself to monitoring. So first of all, why quality of service matters. It is literally the most important thing about your database. A database should not just answer queries, but it should answer them fast. It should not just answer them fast, but it should be consistently fast. This is how you can build reliable, high-performance, cost-effective distributed systems at scale, whether it's small scale or large scale. You need those characteristics. And the reason that quality of service matters so much, in addition to those things, is that quality of service is literally the database's job. You have a database for a purpose. It's not to spin your disks and keep your CPUs warm. It is to answer questions, to store data and to answer questions about that data. And so when we define whether the database is doing its job or not, which is what monitoring is about, we really need to ask, are queries being served accurately, consistently, and correctly? All sorts of things about internal buffers and caches and, read operations and write operations and things like that, interesting, but not the definition of whether the database is doing its job. If you want to monitor your database, monitoring is an outcome of measuring, and above all, you want to measure the performance of queries, not of cache hit ratios or CPU utilization or things like that. Again, those are secondary. You really cannot monitor whether the database is doing its job well unless you measure those the quality of the workload. So I've talked a lot about this. There's some links later on. The slides are already published online. In fact, I'm displaying them from online right now. I'll have a link and a QR code at the end so you can go get these. And there's things like other talks that I've given and stuff like that where I go into this more. But for the last decade or so, I've been harping on this consistently. You've got to measure work and whether it's getting done. So what is quality of service? And to understand this, we have to approach this problem from the perspective of a user or a client or a customer, or it's something outside of the service itself. It's whoever or whatever is sending those requests that we want to know whether they're being performed well or not. So quality of service is that when I send I or a customer or a user or anything like that, send a request to the service, I want it back, and I want it back fast. Everything else is your problem. I don't care about your capacity planning issues. I clicked to post a tweet, and I just want the tweet posted. So you have to adopt that user's mindset to understand what they care about, which is that you're there to serve them, right? And the definition of performance here is latency. So this is a very formal, there's lots of formal math underlying this. And in fact, in a minute, I'm going to show you equations just to illustrate that. But there's a crisp definition here that we can wrap our heads around, latency. It's how long an individual request takes. Okay, so it's got units that we can measure. But in addition to those individual requests, we can't care just about individual requests because we have to talk about things like consistency. And consistency is about a population of requests. So we have to care about all of them. So as a user, if I'm sending a request to your service, if I am an application developer or an end user, and I've sent a query to Postgres, I individually want it to return fast. But as the operator of the service, we have a population of users. We have a population of customers. We have many applications connecting to us. And so we have to care about all of them in the aggregate, which is why I've got a picture of a flock of sheep, right? We have to take care of all of the sheep. And we have to make sure that that population of requests is served with good quality. So that's workload. That population, collection, plurality of requests is workload. And how we talk about that quality of service is in aggregate statistics, in population statistics rather than one by one by one. So workload, another thing about the workload is that it's the interaction between the application and the database. In this case, it's the interaction between the users or customers of a service and the service itself. So it's what crosses that boundary between these two separate worlds. And what we want to do is measure across that boundary. It's a really interesting boundary for a lot of reasons. In the database's case, there's like 5 different things that make it special. If you think about what connects to your database, it's mostly software that you probably are writing yourself or that your engineers are writing themselves. So it's not commercial off-the-shelf software in a lot of cases, but it's software that you can change. You can change its behavior. And it's crossing the boundary to Postgres that you didn't write yourself and that most of us would find very difficult to change if we had to. It's the boundary between stateful and stateless. Most of the time we're delegating all of our state management to the database, which makes our non-stateful applications easy and simple to reason about in comparison. We're putting the hard work in the database. There's a bunch of other things, kind of differences between the application world and the database world that have one set of characteristics on one side and another set on the other side. And what we're really doing is we're making a bridge across that boundary. And that's where all of the interesting and fun stuff happens. And it's also where if you measure and you dig into those measurements and extract insights out of it, it's where you can learn stuff about your application and your database and how they interact that you can't learn anywhere else. You can't learn that from just looking at the database side. You can't learn it just from looking at the application side. You learn by looking at what crosses between those two. So quality of service has 4 metrics that really define it. And 3 of these metrics are tightly related together in a relationship called Little's Law that I'll show on the next slide. The 4th one is simply the error rate. So there's a popular performance method called the RED method that made an acronym RED by sort of using alternative words that had those first letters. I formed CELT by taking the sort of canonical performance metric names here: concurrency, error rate, latency, and throughput. I wished that I could order them in a different order and make a word out of it, but whatever, sacrifice everything to make an acronym that you can pronounce right. And those 4 metrics really qualify and characterize quality of service. So concurrency is the number of things that are happening at a time. This is a little bit different to what we think about in terms of like multi-version concurrency control or other meanings of the word concurrency within the database. But in the workload sense, concurrency is how many things are happening at a time. Error rate is just the number of errors, the rate of errors over time. Latency is that response time, as I talked about it previously. And throughput is the number of requests over time, so the rate of requests. And you can look at these things over intervals of time, which is the typical way of doing it in time series metrics. So you define an observation window. For Vivid Cortex, it's 1 second. For most monitoring systems, it's probably something more like 1 minute or 5 minutes. But you have this observation interval, and you calculate statistics, either averages or summary statistics, over that window of time to characterize your quality of service of your workload. So one of these metrics, concurrency, is this golden metric. It's really magical, and it shows up everywhere you look in every formal description of the laws of system performance. And it just so happens that it's also equivalent to demand or load. If you're familiar with, well, you're already familiar with this metric. It's called a lot of different things. So Unix load average is kind of a very weirdly time-decayed average of concurrency. There's lots and lots of other things that are either concurrency or directly equivalent to concurrency. And you don't need to know anything about this math, but it's just there for those who kind of want to follow that trail through to where it goes. But there's Little's law relates all three of these together: concurrency, throughput, and latency. And concurrency is the unitless, dimensionless metric of how much work a system is performing over time. So a lot of times people will use throughput, the rate of requests over time, as a definition of load, but it's not a very good definition of load because requests are not all the same. There's short requests and there's long requests. There's ones that don't cause much work. There's ones that cause a lot of work. But concurrency is unitless. Every unit of concurrency is equivalent to every other. Okay? So aside from these four metrics, when I talk with people about this, they often say, well, what about CPU utilization? What about memory utilization? What about disk throughput? What about, and there's all of these other kinds of things. And again, those are important and useful, but they are not performance. Performance is whether your users are getting what they want, not whether your systems are struggling to provide that. But they are useful, right? So why do I say that they're not performance? So let me tell you a little war story. Before I founded Vivid Cortex, I was a performance consultant. I happened to do most of my work around MySQL, and this was in the days when MySQL had basically been built on single core servers, and suddenly most of our customers, this was around 2008, 2009, were running it on multi-core servers. And first it was 2 core or 2 CPU. And then it was 4, and then it was 8. This happened pretty quickly around that time. Commodity hardware started to get multi-CPU pretty quickly. And as systems, scaled to 4 CPUs, MySQL would run on it. It wasn't really designed for it very much. But as customers would, refresh their hardware, almost without even wanting to, essentially the default purchasing options were now 8 cores and 16 cores and a lot more memory. And there were a lot of internal scaling issues in MySQL at that time. A lot of mutexes, global mutexes, that, just things that were built with sort of a low concurrency set of assumptions. And now it was being deployed in high concurrency. And people would upgrade from 4 to 8 CPUs and get severe performance problems. And this made no sense because they had just added a whole lot more power to their server, right? Basically the database was spending all of its time fighting with itself. And what confused them the most, they would come and they would say, performance is terrible. Like, we have all of these problems. Everything is timing out. Everything is really slow. So they were correctly identifying performance in terms of slowness and fastness. But CPU, there's tons of free CPU. I mean, CPU is it's basically idle. Like, what is going on here? MySQL itself was kind of, there was some turmoil in the company. It was sort of being acquired and things were happening. And there wasn't a lot of forward progress on the database server for about a year or so while all of this stuff kind of worked itself out. That was the opportunity for me and my colleagues to produce some performance patches that did some relatively simple things like optimizing a couple of the mutexes away, splitting them up, like getting rid of totally global mutexes and breaking them into more fine-grained ones. And the performance improvements were massive because that was like the bottleneck at that time. And so we would say, well, why don't we, this is clearly, like we profiled it and this is clearly the problem. And clearly the solution. It's not anything that you're doing wrong. You didn't design your schema wrong. Your queries are fine. Your indexes are fine. It's not your fault. It's that this database is not designed to run under this concurrency of workload on this highly parallel hardware. And the only fix for this is to fix the server, and not what tuning or queries or anything like that. So we have a patched server for you that's going to be much faster. So people would go, please do it. I'll try anything at this point. So we would put the patch version of the server on, and CPU would immediately get busy. And a lot of people would get really nervous about that. Performance would be great. And they would go, what have you done? My CPUs are now like 60% busy. I'm really worried because they were 2% before. Calm down, calm down. You're using CPU, but that's what it's there for. The reason the CPU was idle before was because everything was sitting and waiting on a mutex. The reason that your CPUs are hot now is because all those CPUs are doing work. So that story kind of illustrates why performance is not the same as things like resource consumption. Right? So long tangent, more story. This is exactly why I say it's so important to look at whether the work is getting done and not to get distracted by some of these other things. They have a place. They are resource metrics, and they can tell you a lot of really valuable things. And you should measure them. You should not ignore them. But they need to be kind of put in their rightful place in sort of the hierarchy. They're one step lower in the hierarchy than looking at the workload. So this workload generates demand. There's a certain amount of work that is just sort of like inherent to the workload. And that generates demand on the resources. It consumes CPU cycles, memory traffic, like all of these things, right? And there's 4 of these key resources: CPU, memory, network, and storage. And the way that they respond to that demand often either explains performance problems or points you somewhere else. So I'll show you next how to figure out if resources are adequate or not. So the reason that you need to measure things like CPU, network, memory, et cetera, is you need to know whether you have adequate resources to meet the demand of the workload. Okay, so there's 3 golden signals, again. I borrow the term golden signals from the Google SRE book. They have what they call 4 golden signals. They're not, I don't mean to be too pedantic, but those golden signals are sort of confusingly named kind of overlapping, sometimes combinations of things. And it's often really difficult for people to figure out what the difference, for example, between traffic and saturation is. So I'm using, again, things that are like canonical definitions of performance metrics. And Brendan Gregg has put together a handful of resource and server-centric ones called the use metric, use method, utilization, saturation, and errors. And when you look at any system or subsystem, its components or whatever, you can apply this method and figure out if that system or subsystem is struggling and exactly where. And if you follow this link from the slides, he's got this really long page with a great table of contents for every kind of system, every kind of operating system, hardware, configuration, whatever you can ever imagine, and how exactly to apply the use method to that. So it's a great way to kind of conceptualize and define the problem space of looking at the hardware and other resources that support your workload and figuring out whether they're adequate or something is wrong. All right? And so when you put these 2 worlds together, when you put the externally facing, customer-focused, workload-centric mindset together with the internally focused, do I have the resources to actually get this work done, then you get what I call the Zen of performance. And you unify both of these worlds of the external singular customer with their singular requests that they uniquely care about, with the internal world of operating a service that has to handle a plurality of these things and provide good aggregate performance to all of them at the same time. And you take those metrics and you put them together, CELT and use metrics together, and you get the 7 golden signals. And errors is actually defined in there twice, because there's 2 ways that you need to think about errors. One of them is a request error, and the other is an internal resource error, like a hardware error or something like that. So there's actually 2 kinds of errors, which is I didn't combine those into a single E. So you put those 2 things together, and you get a total system worldview mindset kind of way to look at performance. So I keep saying system, and when I think of system, I actually think of something pretty specific. It's easy to say, the system is, for example, the server that runs my database. I think a system, to be really complete and useful, the notion of a system needs to extend out and include everything that's interacting with our server and our service, which is all of our users. And in fact, our users are even interacting with each other because, for example, placing demand on the service is creating back pressure out to other users. So we may not, as users, we may not be aware of each other when we tweet, but my tweet affects how quickly your tweet gets posted. So we all are interacting. And when we think about that, that's the total system kind of worldview. And we need that. We need to think about it that way, because otherwise we're going to have a limited view of where problems come from and how they arise. And systems have behavior that arises organically from the interactions among their parts. If you haven't read the Chaos Engineering book it's a short, 70-page ebook from O'Reilly. It's about a year old. And you can download it for free from O'Reilly. If you haven't read that, it's a really great, in the first chapter, maybe the second chapter, there's a really great description of a system responding to workload and an error and network disconnection. There's a story of a mobile app that gets disconnected from the network and queues up a bunch of requests. When it gets connected back again, it sends all the requests through. Those trigger a caching behavior that is basically a circuit breaker to shed some load. The load suddenly drops. The system goes idle because the load drops. An auto-scaling thing says this one is idle, it's not needed anymore. It scales it down, shuts down part of the service. So it's this great description of how a system behaves. And every single part of that system is totally rational locally. And yet when you put it all together, it's kind of pathological behavior. So this is why we need a systems mindset when we think about performance. This is why we need to be thinking about our users and not just about our indexes, right? And if we're not monitoring all of these things, then we're not really monitoring the system. We're just monitoring the parts of it. So this is why, for example, the old way of when somebody said, I'm getting complaints, I'm seeing reports of outages, people are asking if it's down, and the DBA goes, CPU looks fine to me. That's why it doesn't cut it, because it doesn't matter if your database is theoretically available. It's up. There's been no downtime. Doesn't matter. As Charity Major says, nines don't matter if your users aren't happy, and you really need to be thinking about all of those things at the same time. So what this brings us to is mental models, which is one of my favorite things, and I'm probably, since I'm not a researcher on this stuff, and there are people who research this stuff and actually know what they're talking about, I'm probably full of beans. But I think a lot about mental models because I'm a programmer, and then I became a database guy, and then I became a consultant, and then I founded a company, all this stuff. But that programmer is still there in me. And I think about systems, I think about the code that I wrote, and I write that code or design that system like a sales compensation plan or whatever it is with a mind to how I think things work. and I'm trying to create incentives or trying to give instructions or whatever it is to create a desired outcome. And when it runs in the real world, I'm always wrong. This is why I need a debugger. I started programming in Visual Basic 6. VB6 was glorious and beautiful, and nothing has ever come close to the perfection and beauty of VB6. And I'll tell you why. Because it had an interactive IDE where you could start writing the code, get a line or two in, and go, what's that going to do? And start debugging before you had even closed your if statement. And start stepping through, like one line or one part of a line behind your cursor, and watch what was going on in your variables and context while you were doing it. And you write so many fewer bugs that way when you're debugging as you, literally before you have even completed writing the program, you're seeing it run. That real-time feedback tells you the difference between the system that you are constructing and your mental construction of it, which is always wrong. Right? So we have the system as we imagine it and the system as it really exists. And those are always different, always. So we can try to bring them as close as possible together, but as humans, we do not operate directly on the world. We operate on our concepts of the world. And so when I create a sales compensation plan, which I don't have to do anymore because I'm not CEO anymore, but when I did create a sales compensation plan, it was designed to create some incentive, and then the salesperson would do something different, right? And so that was my clue that my mental model of that salesperson's motivations and behaviors was not accurate, right? So our mental models are always wrong, and trying to tune our mental models and get them closer to reality is extremely important. We should always be trying to do that. By the way, that's a core concept in most religions and philosophies in the world, including Buddhism and Christianity. I mean, you could just name them all. They're all about getting yourself as close to the truth as you can. So it is as programmers. So here's Pete. I don't know Pete, but I saw his tweet. Somebody retweeted his tweet to me. He's been developing for a quarter of a century, and he's trying to figure out how 5 lines of code is misbehaving. And I'm pretty sure we can all empathize with this, right? So, his mental model is wrong. Similarly, we get mental models of our databases. We think we know how they behave. We think we know what their workload is, and we're always wrong. So we think this first one actually came from a customer of ours. I went to a customer, did an on-site, did some training. I had a whole bunch of developers in a room and Vivid Cortex up on the wall, and I had the profiler that floated the most time-consuming queries to the top. And there was one developer who kind of had his head to the side like this. And it was that developer that always knows which skeletons are in the closet and where all the bodies are buried, because they've been there forever. And it's the person that everybody goes to ask, the arcane details of something that was there before they joined the company. And he goes, what is that query up at the top? I mean, I know what that query is, but what does it mean that it's up at the top? And I start giving him the blah, blah, blah description of it. I'm like, well, so we can see that if we hover the mouse over here, we can see that it's executing on average 4 seconds per second of wall clock time, which means the concurrency is 4. So that means that effectively, like all day, every day, there's an average of 4 of these queries running at a time. And he goes, stop, stop, stop. That's baloney. That is a once-a-day cron job that should run for like 30 seconds. And it runs at 4 a.m. I mean, I wrote it myself, I know. And I'm like, well, the evidence is that this query is running basically continuously all day, every day. And he goes, something is deeply wrong here. He goes, I'm going to leave. He closes his laptop. He leaves the room. A couple of minutes later, he comes back and he goes, I dug into that cron job, and it was supposed to process yesterday's data every day, which should be really quick. But I left off the where clause, and that was a few years ago. And now, it's been reprocessing all of history. And now it's getting to the point where it's running for 4 days every day, which explains why there's 4 copies of it running at a time. So his mental model was that this thing is supposed to run and do yesterday's data, but it's doing all of history, right? All of these others are things that I personally have done, or our customers, or when I was a consultant. These are all things that I've seen many, many, many times. And the only way to refine your mental models is to measure. and see where they're wrong, right? So anything that you don't measure is something that you're imagining, and that's what your mental models are. And when you measure that workload, when you measure the application to database interaction, you're guaranteed to be surprised. Guaranteed. Every time. It does not fail. It always happens. So just like Pete, that difference is there and it's real. And when you get a debugger on it, or when you get, that quarterly review with the salesperson, or you get Vivid Cortex and you look at what your queries are doing, or whatever, you're going to find that you didn't know something. So to bring this back to monitoring, question for you, are you monitoring workload quality of service? A lot of people are not. A lot more people are now in Postgres than they were previously. So previously, you had to use pgFoin or pgbadger and the query log to get any measure of queries at all. Now you've got pgstat statements, and it's basically standard, and people are using it widely. So it's great. But still, a lot of people are not actually using it. So there's 3 primary ways to measure workload. And the one is that you can turn on logging. And the good thing about this is that it works. And it's basically the first thing that every database builds in, ever, builds in a query log. And that's pretty much the first way to measure what it's doing and monitor what it's doing that is ever built into the database. The bad thing is that especially when you have low latency, high throughput queries, you add a ton of overhead, and it becomes unsustainable. So therefore, because of the operational and performance hazards of doing full query logging, we turn to number 2, which is to use things like pgstat statements. The great thing is that it is built in and native in the server, and tells you everything about the server. I want to pause there and kind of go on a little bit of a tangent. A lot of times people will use like an APM product that instruments their application code, which also instruments everything that it is sending to the database. So it's instrumenting and measuring most of the database calls. And that is better than nothing, but it is not a full fidelity representation of what the database is doing. And the canonical way that I always kind of dig into people when they say, but I already have APM, why do I need to monitor the database separately? Is I say, well, have you ever dug into your APM product and you drill down into a slow transaction and you find a 10-second query that when you run it is 12 milliseconds? And they go, yeah, that happens all the time. I find slow queries that shouldn't be slow. And I'm like, yeah, well, that's because something outside of the application context is also talking to the database. So one of the neat things about databases is that they have lots and lots of customers. Not only do they have lots of customers, but they also have backups and maintenance jobs and ad hoc scripts and the Excel plugin that the finance department has in a spreadsheet and all of these kinds of things. And if you're just looking at what your application is instrumenting in the application code, you're seeing a very partial worldview. So the nice thing, to get this back to this slide, is that something like pgstat statements will tell you the totality, not just one application's point of view of what it thinks the database is doing, but everything that the database is really doing. So it's super important that you take the database's word for the work that it says it's doing, and not some application's perspective on it. The downside of these is that a lot of times it doesn't exist, it's not enabled, or it would require, for example, a restart to enable it, and you are now sort of stuck because you have to, you've got a system that's performance critical and production critical, and any kind of a restart or something like that is a major event to think about, and yet you need to measure it. So you need to measure it, and yet you can't without causing problems that you're worried about. The other thing, and I'll come back to this a little bit later, is that it gives you aggregate data. So for efficiency, it's aggregating all of the statements over intervals of time, essentially. If you poll it, you're getting basically intervals, you're getting deltas over intervals. But those are not individual specific query executions, and I'll come back to that a little bit later. So the other way, in my career, I've seen basically these 3 ways to do it. The other way is sniffing the network traffic. That is the primary way that we like to do it at Vivid Cortex. We do support all 3. but we built the query network traffic sniffing first, and then we built the other things later. Sniffing the network is great. You are literally measuring the medium of that application database boundary of that interaction. And it's possible to do it extremely efficiently. It's technically hard, but you have near zero overhead on your database server, and you have a lot of fidelity. And you're getting the full stream of events, not just sort of aggregates of them. It doesn't have access to the database internals, but of course you can supplement that by also looking at the database internals, and you stitch those things together and you get a fantastic view of the database performance. So now that we have this data, what do we use it for? Well, we can use it for sort of bread and butter monitoring. Is the service alive? Is it providing good quality of service? We can also use it for diagnosing performance problems. And this is where I have a heavily, heavily performance-focused take on monitoring. Nagios scripts don't do much for me. They just tell me whether the thing is alive. I really want to know, is it performing well? And help me, give me the data and the tools that I need to drill into the performance problems, both ones that are really glaring as well as the ones that are kind of, just emerging and they're a needle in the haystack, and we pull that needle out of all of this noise of the workload. Workload monitoring, by the way, is a big data problem. There's a lot of queries happening in most systems, so pulling the needle out of that haystack is an interesting set of challenges, but really worthwhile. This is where you find all of the problems that are emerging that one or two of your customers are suffering from every now and then that are going to turn into something much bigger later. So in terms of proactive monitoring, digging in and figuring out what your application and database behavior really is about as proactive as it gets. So there's three kinds of performance problems. And these are focused on the quality of service and the impacts of the quality of service. So the first one is that latency is too high, either individually or in aggregates. Something is not getting good, fast performance. The second kind of performance problem is that you're spending too much money and your finance team is unhappy with you to provide an acceptable level of performance. It can go the other way as well. Maybe you're providing an acceptable level of an unacceptable level of performance, and it's because you don't have enough resources. So a lot of our customers come to us initially when they're throwing money at the problem because they don't know another way to solve it. So they're suffering from, performance problem number two, that resource usage is too high. And then the last one is that whole systems view where we have something suffering because something else is being abusive. All three of these kinds of performance problems are possible to diagnose by looking at either the workload metrics or those internal use metrics and then digging into it from there. And all of them are caused by four categories. So I like to break things down into small numbers of things that you can kind of think about and have a kind of a worldview of how to subdivide the problem into something that's manageable. So these are my four categories of performance problems that I've seen things always fall into the causes. So number one is you're doing work that shouldn't be done, or you're asking the system to do work that shouldn't be done. Number two is something is being done more often than it should be. The third one is that something is being done, but it's taking too long. And then the last one is that we have starvation or stalls that are causing things to be too slow. And when I say too slow requests here, what I really mean is that the request is asking for too much work. So for example, a query that doesn't have a good index is looking at a bunch of rows that it shouldn't look at. And the one tool to rule them all, the one thing that can help you dig into all of these is a profile of the workload. And you can get this from PG Badger, you can get it from Powwow, you can get it from Vivid Cortex, and get it from New Relic. Basically, every tool that is effective in helping to diagnose performance problems has one of these built in. And profilers are universal. They're obviously profilers in programming languages. We're doing exactly the same thing here. We're looking at the hotspots. So it groups related things together because the workload is big and there's a lot of noise there, and we're trying to reduce it to a smaller set of things that we can actually conceptualize and reason about. And then we rank them and float the hot ones to the top so we can look at them. So a bigger view of that, this is from Vivid Cortex, but it's going to be a similar view in all of these kinds of tools. This is most time-consuming queries. The way that we have designed this visualization is that the dark blue underbars on the left-hand column are a percentage of the total. So if you see the column around in the middle that says starts with 28.89%, those underbars are exactly the same thing. So you can see we've ranked things by their percentage of the total amount of time spent by all of the queries in the database. So we can immediately see that our first query on the top is consuming roughly 30% of the time spent in our database. So right away we know if we want to reduce the amount of time that the database is spending running queries, this is the #1 candidate to look at. We also see the shape of it. So we see that time consumption is concentrated in a few spikes. It's not uniform. The second query is extremely uniform. It's also very time consuming. By the way, this is a handful of different kinds of databases here. There's something of everything. There's some MySQL, Redis, Postgres, and MongoDB all together in this view. So this is an entire application and set of servers. I cut off parts of the user interface that show that. But just know that that's all there. So we can use this to find a lot of different kinds of performance problems. So we can profile not only by total time, but we can also profile by frequency. So we can find the most frequent. So I'm going to break these next couple of slides down in the same order as I showed you those performance problems and causes of them. So here we're finding needless and too frequent requests. And those are the top 2 from my list of 4. And if you profile by frequency, those will float to the top. So you will find useless queries, like something that a driver is doing, like saying, hey, is the connection open, before sending a query, which is a look before you leap pattern. You'll also find queries that maybe should be prepared and reused, or you'll find things that are one by one instead of being done in a join or in an aggregate query. You'll find all of those kinds of things. You can also find requests that are too slow, that have too high latency, by looking at the latency or by looking at the which is the time-consumingness of them, or by looking at descriptive outlying tail metrics like the 99th percentile latency. The next question is, when something floats to the top, how do we know if it's actually worth optimizing? How do I know if that top query is really worth optimizing? And so if you look at a couple of different dimensions of this together, then you can answer those kinds of questions. So for example, if we look at the additional columns here, you scan your eyes down to the one near the bottom, this select star from guestbook order by time descending. The average latency of that one is 9.7 minutes. It doesn't happen very much overall, but everybody is getting a terrible experience from that. And it's so long that it should be totally possible to put an index or a query rewrite on that and make it dramatically shorter. So that's low-hanging fruit. So you basically look at the combinations of these different metrics and see, is there something that is just like way outlying in one of these dimensions? And that's how you can prioritize. So rule of thumb, a couple of rules of thumb, to reduce the resource consumption on your server and make available more resources and reduce collateral damage and starvation and things like that, try to reduce the percent of total of the most time-consuming queries. And to make customers happy, look at the 99th percentile latency or the average latency, whichever is available to you in the tool of your choice. And then from there, those are all aggregates, right? So we're all looking at queries in bulk. Each of those rows in that profile represents a lot of things grouped together. And it's good because it kind of focuses us in the right neighborhood. But from here, we need to drill down from the neighborhood to the individual, we've gone from a city block to an individual address. And there you find that those averages are misleading. Even things like the tail latency, like 99th percentile latency, is misleading. When you get individual requests, then you start to find out the truth. So you need to drill, if you're looking at PG Badger, you need to look at the log itself. You literally need to just look at the log and individual lines in that log. Because you need to see individual specific things like the parameters in those queries, whether they were all touching the same customer, or they came from the same origin IP address or something like that. And you need to look for patterns. So ideally, you can visualize. When you visualize, things just immediately pop out that you will never find. This is not a contrived example. I actually just took this screenshot this morning from the same screenshot that I showed you before. I just clicked on the second query, and immediately this just popped up on the screen. So this is a real application, and it's got some pretty interesting patterns that you would never know if you weren't looking at collections of individual requests. Each little gray circle represents the latency of an individual request, and time goes from left to right. So visualizing and then inspecting those individual requests to figure out what the heck is going on with that one. Not with the group, but that one. Then you get an individual query that you can run an explain plan for, et cetera, et cetera, et cetera. So if you find a bad query and you don't know exactly what to do, sometimes it's really obvious, like this query needs an index. But if you find a bad query and you want to fix it, you have to ask yourself some questions that a tool can't answer for you, at least not today. At least we haven't built, and I don't think a tool is built yet that will give you all of these answers. But you have to answer questions like, how slow is too slow? How fast should I expect it to run? What is it doing? Is it working or is it waiting? Where's the time going? And there's only 3 possible solutions. So we can eliminate work, which is that needless work. We can reduce work. For example, rewriting a query to do less CPU computational intensive stuff. Or we can drill down into the subcomponents, find the biggest subcomponent like fetching or waiting on a lock or something like that, and then optimize that away. And I'm running a little bit short on time, so I'm going to speed up a little bit. Although actually, I guess I'm the last session, so if you don't mind, I'll take a few minutes so that I can go through the last little bits here. So this is all general. Like I've told you very little that's specific to Postgres or any database at all. But the specifics really do matter. And every technology has things that tend to be the problem repetitively. I call them sharp edges. And they usually arise from some limited resource or from something in the critical path. And every technology has them, and we trip over them constantly, so we know what they are. So some of the sharp edges in Postgres map to specific metrics that have found their way into statistics views, and I've got a few slides here to focus on those. So my recommendation is that you focus only when it comes to things that you look at. Let me pause a second. So when I look at a server, I don't just start looking at all of the graphs and asking what does each graph mean, because that's kind of the tail wagging the dog. It's kind of coming into the problem backwards. I want to have a theory about the system and about what's happening, and then I want to ask myself, what data would prove or disprove this theory? And then I go look at that metric or that graph, and I go, nope, it's not that. So what else could it possibly be? So that's kind of approaching it with a theory and trying to prove or disprove my theory. And it results in a lot fewer false positives and wild goose chases than just scanning through pages of graphs. So these are the things that I think you can start from. They're a starting place where you don't have to have a theory. These are diagnostic metrics that can tell you whether there is a problem and lead you to the next step. Okay? So if sequential scans or index scans are higher than normal, then you probably have a problem. And you could, for example, go look for a query that is new, that is newly introduced to the system, that is not well indexed, for example. Right? So these are a few of the things that I would recommend looking at. I'm not going to talk through all of them, but they're here for your reference in the slides. These are how you can detect if there is a query performance issue kind of at the highest level without even looking at a profile of the queries. You can usually detect these things even in the aggregate. You can also detect whether there is a capacity or a resource constraint by looking at some of these metrics. They're very sensitive. Replication will delay if replication doesn't have enough resources to keep up. You don't know exactly what is making it not keep up, but you can, it's like, checking for the next steps from there is a much narrower search space. Same thing with checkpoints and connections. And then finally, vacuum. And auto vacuum is a set of processes that can be very finicky. and is absolutely critical. You know, if it gets just over the tipping point and kind of gets on the wrong side and can't catch up, then all kinds of cascading problems sort of go from there. And this is how you can tell whether vacuum is working well or not, and next steps for digging into why. Okay, so I'll wrap up. I think I have, yeah, I'm right on time. My timer says 0, so. So in conclusion, monitor workload and the external customer experience of your service, not just, you know, is it up and does there seem to be enough CPU and things like that. Measure that work getting done. That's what your database server is there for. That's what you should measure, and insist that it does a good job on. Focus on those 7 golden signals. That's a much reduced set of things that will keep you from looking at 300 things and not knowing what to do next. Drill down into the individual queries and requests and cover the basics of the things that tend to be problematic, and make sure that those are, you know, make sure that those are happy. So here's a talk that I've given that people have told me that they find helpful a lot. It goes into a deeper kind of structuring of the different types of things that you can measure about systems. Some books that I've written, these are all free, and you can click on the links. Books that are not free but are really, really good. I should put the Chaos Engineering book on here too. And slides, you can snap this and download it, and you can also go to my website. You can tweet me, you can email me, and I'll gladly answer you. So that's all. Thanks.